So yesterday we saw that we can do sum and differences of functions. Today we'll look at products and quotients. The product f times g at x is the same as f at x times g at x, and the quotient f over g at x is the same as f at x over g at x. So pretty straightforward. But when you're talking about the domain and range, especially the domain, and you're doing a quotient, then you have to be aware of what the restrictions are and where they come from. So the very first one, you're given f and g. You're asked to find h at x, which is f times g at x. So once again, that would be f at x times g at x. F at x is x plus 2 all squared minus 5. And that's multiplied by g at x, which is 3x minus 4. And then it says, you could multiply these out if you wanted to, but it wouldn't really be any simpler than what we have right there. So let's just leave it as is. And for the domain and the range, we will use our graphing calculator and put this equation in, see what it looks like. So I'll open up a set of brackets for the first factor, and then within that factor there's another set of brackets for the x plus 2, which is squared, minus 5. So close that first set of brackets, and then the second set of brackets is where we have our 3x minus 4. And we'll go zoom 6 to set our windows to their standard settings. And we see a partial graph. If we make our y maximum a little bit larger, or maybe we'll try zoom 0 for zoom fit. Let's try that again. Let's go zoom 0 for zoom fit. This graph is basically a polynomial function. It's a third degree polynomial function, because if you expanded out the x plus 2 all squared, that would give you an x squared term. And when multiplied by the 3x in the other factor, that will give you a 3x cubed initial term. So this is a third degree polynomial. And because of that, there are no restrictions on either x or y. Our domain will be all real numbers, or from negative infinity to positive infinity. Our range will also be all real numbers, negative infinity to positive infinity. For this next one, again, we're doing the product. H at x is f at x, which is x squared, times g at x, which is the root of 4x minus 5. And in this case, there will be restrictions on x, because the second factor is a radical. What's under the radical has to be greater than or equal to 0, because you can't take the root of a negative number. So, to find our restriction on x, again, the radicand has to be greater than or equal to 0. So 4x has to be greater than or equal to 5. X has to be greater than or equal to 5/4. That is our domain. Once again, we can use our graphing calculator to confirm this and also help us with the range part of it. So if we go x squared as our first factor times the root of 4x minus 5. Again, I'll go zoom 0 for zoom fit. Doesn't really give us a good look at the graph. Let's go zoom 6 to set our windows to their standard settings. So it kind of looks like this graph starts in the first quadrant, not on an axis, right? However, if I go zoom decimal, zoom 4, kind of shows us the same thing. Let's go into the trace mode. We said that this graph starts at positive 5 quarters. X has to be greater than or equal to positive 5 quarters. So once we're in the trace mode, if we let x equal 1.25, which is positive 5 quarters, that is the value of y being 0. That's where this graph starts. That is where this graph starts. It starts at the point 5 quarters, comma 0. Because when x equals 5 quarters, the radicand will be 0. The square root of 0 is still 0, and 0 times x squared, well, actually it's 0 times 5 quarters squared, but it doesn't matter because you're multiplying by 0. So that's where this graph starts. It starts at the point 5 quarters, comma 0. So because of that then, our domain will go from 5 quarters up to positive infinity, and our range will go from 0 up to positive infinity. Right? So quotients of functions, you've got f and g. You want to determine the equation of h, which is g over f at x. So again, h at x would be g at x over f at x. So g is 2x plus 6 over f, which is x squared plus x minus 6. And back in chapter 9, we worked on rational functions. Right? We said sometimes there's vertical asymptote, sometimes there's points of discontinuity, sometimes there's a horizontal asymptote. In this case, the degree of the top is less than the bottom, which means that the x-axis will be a horizontal asymptote. To get the rest of the information, we will factor. There's a common factor of 2 on top, which leaves us with x plus 3. On the bottom, you'll have x plus 3 bracket x minus 2. And then the x plus 3's cancel. So we'll be left with 2 over x minus 2. So remember back from chapter 9, what this tells us is that you will have a point of discontinuity at the point where x equals negative 3. Our non-permissive values come from the original expression. Negative 3 is a restriction on the original expression. But because that factor canceled, it means that there's a point of discontinuity at x equals negative 3. And then to find out what the y value is, we'll let x equal negative 3 in the simplified expression, which will give us 2 over negative 3 take away 2, or 2 over negative 5. So we're going to have a point of discontinuity at negative 3 comma negative 2/5. Approximately there. Because we have x minus 2 as a remaining factor when we simplify the expression, that means there will be a vertical asymptote. At x equals positive 2. So we can put that in there. Now again, we said because if we look at either the original expression or the simplified one, the degree of the top is less than the bottom. So that has meant in the past that the x-axis is an asymptote. But let's check that, because we can use our graphing calculator and put that in. So y equals, we'll use brackets. Our numerator is 2x plus 6 divided by, in brackets, x squared plus x minus 6. Zoom 6 to set our windows to their standard settings. And yes, by looking at the graph, we can see that the x-axis is a horizontal asymptote. We can also confirm the point of discontinuity. If we go into the trace mode and we let x equal -3, there is no y value returned, which means that that point is not on the graph, not part of the graph. So that confirmed that our point of discontinuity is at -3. But we want to put our horizontal asymptote in there. The graphing calculator, using that, also confirms that the graph is in the top right-hand quadrant and the bottom left-hand quadrant. And those quadrants are formed from the two asymptotes. Right, so we've got this one here. And you certainly could, if you wanted to, generate a few points to give your sketch a little more accuracy. For example, you could find the y-intercept by letting x equal 0. When x is 0, and we use a simplified expression for this, you're going to have 0 take away 2, which is -2 on the bottom, and 2 over -2 is -1. So that tells us that the y-intercept is at -1. So you could use that definitely. Now this one did ask us to sketch F, G, and H. I just put H on there, but sketching those other two is not difficult. But we do want to state the domain and range of H. And so when you're doing this, most of people take into account the vertical asymptote, but what a lot of people forget is the point of discontinuity. So if I use set notation here, our domain is all values of x, such that x cannot equal either -3 or +2. -3 is where our point of discontinuity is, +2 is where our vertical asymptote is. Same thing with the range. Most take into account the horizontal asymptote, but they forget about the point of discontinuity. In this case, y cannot equal -2/5 or 0, but all other values are possible. So don't forget about the point of discontinuity. Okay. So on the next page, again, we want to go F over G. So it's x plus 2 over x squared plus 9x plus 14. Again, the degree of the top is less than the bottom, so the x-axis will be a horizontal asymptote. To see whether this graph has a point of discontinuity, vertical asymptotes, or a combination of those, we factor the denominator, which factors to x plus 2, x plus 7. The x plus 2's cancel, and you're left with 1 over x plus 7. So because the x plus 2's cancel again, that means there's a point of discontinuity. At -2, because that factor of x plus 2 cancel. And when you're looking at the restrictions, you have to look at the original expression. And when you let x equal -2 in the simplified expression, the denominator becomes -2 plus 7, or 5. And that's under 1, so there's your point of discontinuity. We're going to have a vertical asymptote. at x equals negative 7 because we still have a denominator of x plus 7. So again, we have a vertical asymptote at negative 7, a horizontal asymptote along the x-axis where y is 0. I've got a point of discontinuity at the point negative 2 comma positive 1/5, so just above the x-axis. This tells us that the graph, the one arm of the graph, the one branch will be in the upper right-hand quadrant. We could, if we wanted, generate a few more points. For example, if we let x equal, let's say, negative 6, the denominator becomes negative 6 plus 7, which is 1. 1 over 1 is 1. So that confirms at that point negative 6 comma 1 is on the graph. You could also find the y-intercept by letting x equal 0. That'll give you positive 1/7. But there's that branch of the graph. And the other branch should be in the lower left-hand quadrant, which we can confirm by choosing a value of x being, let's say, negative 8. When x is negative 8, the denominator will be negative 1, and 1 over negative 1 is negative 1. So the point negative 8 comma negative 1 is also on the graph. And so there's the graph of h. For the domain, again, cannot forget about the point of discontinuity. You can still use interval notation for this if you want. It would look like this. Our first restriction on x is our vertical asymptote at negative 7. So we could say that the domain goes from negative infinity to negative 7, and then from negative 7 to negative 2, because that's where our point of discontinuity is, at x equals negative 2, and then from negative 2 to positive infinity. You'd have to use 3 intervals there if you want to use interval notation for the domain. Same thing with the range. We'd go from negative infinity to 0, from 0 to 1/5, and then from 1/5 to positive infinity if you wanted to use interval notation. Probably easier to use set notation, but they both work. Okay? They both work. All right, we're going to stop there. And you can do those questions. I also want to go through the chapter 9 quiz, so we will do that now.